In this module, we will begin to dive more deeply into the bands on the GOES ABI and explain some of their various utilities. We'll start back at the table of the 16 GOES channels. Each channel represents a passive observation collected by detecting radiance with the wavelength range denoted by the second column in the table. The spectral response function, or SRF, describes the sensitivity of bands to radiation as a function of wavelength, and it has a maximum value of 1. These functions shown here by the black lines are for the AHI shortwave bands with visible light colored, and then for some additional bands outside the visible spectrum at the bottom. On the top row, you see the spectral response functions plotted as black lines for the blue, green, and red bands. Take the blue band, for example. The radiance observed for channel 1 is influenced by radiation with wavelengths between about 450 and 490 nanometers. However, it is more influenced by radiation closer to 490 nanometers than on the lower end of the range, where the SRF is a smaller value. Channel 2 is evenly influenced by radiation, with wavelengths between about 500 and 520 nanometers. The red band, channel 3, is a wider band that is influenced most by radiation with wavelengths between about 600 and 680 nanometers. Radiation at wavelengths where the SRF is 0 for a given band do not affect radiance observed in that band. The spectral response functions for ABI are plotted here in blue, except for the 2 visible channels in this figure. Shortwave channels 1 through 6 are shown on the top row, and the shortwave infrared channel 7 and exclusively longwave channel 7 through 16 are shown at bottom. For shortwave radiation, we are observing photons that are scattered by the atmosphere, things in the atmosphere such as clouds, or by the surface or ocean. Radiation enters at some angle called the incidence angle, and the angle with the ground that the path to a satellite makes is called the excidence angle, which is 90 degrees minus the angle used to calculate mu in the computation for slant path optical depth. Our goal is to take 2 known quantities and derive something about a third unknown quantity. We know what solar irradiance is, and we know what the satellite senses because it regularly transmits data to Earth. This is an example of an inverse radiative transfer problem. We know the answer, or the radiance observed, and we are trying to learn some properties of the surface or atmosphere that cause scattering on a path toward the satellite sensor. Back to our plot of SRFs, the top panel denotes channels that will detect scattered solar radiation. You can see how the red band is a little wider than the blue band, for example. The faint gray line represents the direct transmittance of the atmosphere as a function of wavelength, with its axis on the right side of the plot. For the most part, the bands are located in parts of the EM spectrum for which Earth's atmosphere is transparent. For example, about 80% of the radiation reflected off the surface in band 1, centered on 470 nanometers, will reach the ABI. The rest will be scattered. Nearly 100% of the approximately 1.6 micron radiation scattered off the surface will return back to space in a cloud-free environment. 5 of the 6 shortwave bands can readily pass through the atmosphere without being heavily absorbed. However, channel 4 is centered in a narrow band near 1.38 microns. We can tell that the band is narrow because the spectral response function is not very wide. At this wavelength, the transmissivity of the atmosphere is near 0, as indicated by the gray line. This is because water vapor absorbs radiation at this wavelength. Obviously then, the purpose of this band is not to detect radiation scattered off the ground or ocean. Instead, its primary purpose is to detect high cirrus cloud. There are many scenes that, using visible imagery, show a variety of cloud at various altitudes. Sometimes, however, cirrus cloud is so physically and optically thin that it's difficult to see in visible imagery. However, by choosing to passively observe radiation scattered in a band subject to absorption by water vapor, we only end up seeing radiation that is scattered by clouds at the top of the atmosphere. We don't see clouds lower down because the 1.4 micron radiation is absorbed and re-emitted at a much longer wavelength consistent with this temperature. We'll see an example of some of this imagery shortly. Let's look at a sample of GOES 17 imagery over the default 1-minute mesoscale located over California. First, we'll look at a morning scene in band 2, the highest resolution red band. What is plotted is the brightness value, which is essentially just normalized radiance, as we'll see in the first lab. Intuitively, the white, or bright areas, indicate where more solar radiation is reflected. An expansive offshore deck of stratocumulus cloud is visible, as well as some reflection off the surface over the Central Valley or in Nevada. There are also obviously some high clouds visible that extend from southwest to northeast in the image. With the morning insolation angle, the higher clouds stand out easily from the background stratocumulus deck because of the shadows they cast on the lower layer. If we look at reflection in channel 4 at nearly the same time, we can see that the reflection of the low-level cloud or surface are no longer visible. You only see reflection off of the high cloud because radiation that passes further down into the troposphere is absorbed by water vapor and so cannot be reflected to the satellite sensor. However, the radiation reflected off these high clouds do not encounter as much water vapor, and it's more likely to reach the satellite sensor. As you can see, this channel is useful for quickly separating cirrus cloud from other reflective clouds or surfaces below. It can be useful for quickly identifying the direction of upper-level flow in a complex scene with many clouds moving in various directions in a directionally sheared environment. Recall the general equation for radiative transfer in a scattering atmosphere. This would apply primarily to all but channel 4, for which we would have to consider absorption and scattering. L0 in the equation was the surface radiance directed upward and caused by reflection of radiation at the surface. However, how radiation is reflected off the surface is dependent upon many properties of the surface and the angle at which radiation is incident upon the surface. The bidirectional reflectance is a function that describes the scatter of radiation coming from a direction theta r and phi r into many different directions theta I and phi I. We won't go into detail about what these functions look like, other than to conceptually describe two types of scatter off the surface. One is Lambertian reflectance. It occurs when incident radiation is scattered isotropically or equally in all directions off of a surface. So like this example that I'm highlighting with my mouse pointer here, these black arrows indicate radiation being scattered essentially equally in all directions. The other is specular reflection, or mirror-like reflection, in which most radiation scattered is focused onto one exit angle. In the real world, perfectly isotropic or specular reflection rarely occurs off the surface, but there are situations in which the ocean may behave in one of these extremes. A very rough ocean may behave more like an isotropic scatterer, especially if the incident radiation is from above. A very calm ocean surface can act like a mirror and focus radiation along a narrow return angle. This appears to the satellite as a locally heightened area of reflectance, known as sun glint. An example of sun glint can be seen from some old GOES 10 imagery from the previous century. Although faint, inside the orange circle, you can see how the reflectance off the ocean surface looks locally higher than in nearby locations that are cloud-free. A clearer example can be seen in more recent imagery from GOES 16. Again, reflectance is enhanced inside the orange circle. You could especially tell that this is caused by sun glint because if you viewed a loop of shortwave imagery, you'll see the area of heightened reflectance move westward during the day as the Earth rotates. The state of the sea surface affects the appearance of sun glint. Shown here is imagery from the Advanced Very High Resolution Radiometer, which was once actually very high resolution for our capabilities at the time the instrument was developed. The region of sun glint off the west coast of Mexico is apparent right here. Compare that sun glint with that from the same location at nearly the same time a few days later. The solar angle is essentially the same, but the sun glint reflectance is much greater and more focused in a narrow region off the coast of Mexico. This heightened sun glint can occur if the sea state is calm and the ocean behaves more like a specular reflector. The variability of the bidirectional reflectance of the ocean surface will again be considered later in the course when we discuss the use of scatterometers for estimation of surface wind vectors. Let's take a look at a couple of other bands next. In particular, we'll look at bands 1 and 3, in the blue visible light and the near infrared. First, here's another look at band 2 from our scene over California. And information, a little snippet on each of these bands is located at websites listed on the next few slides from the University of Wisconsin. And if you want to switch the band number to find information, just replace the 02 here with the number. So, you can do 01, 02, etc., right on up to 16. So here's our red band 2 over California. And here is the same time a few minutes later as imaged in band 1. If we flip back and forth, this is red, blue, you can see that radiation in band 1 is generally reflected more than in band 2. Here's band 1 one more time, and band 2. This is because blue light is more likely to be scattered by air molecules and aerosols in the atmosphere than red light. Therefore, band 1 is often used for aerosol detection, such as detection of dust, haze, or smoke. Channel 3 detects near-infrared radiation. It is not visible to the human eye and is a little longer in wavelength than red light. Vegetation tends to absorb red visible light and reflect the near-IR radiation. Therefore, land surfaces often show up as highly reflective. Notice how in this scene the Central Valley is much more reflective in band 3 than it was in bands 1 or 2. In fact, much of California is more reflective in band 3. Take a look at the true color composite image of the same scene, shown here, and flip back and forth. The highest reflectances in band 3 are where green colors or vegetation appear. In the Central Valley, this is active agriculture. In Northern California, along the coast, and then also through the Sierra, forests reflect near-IR radiation efficiently. In contrast, plants absorb more of the visible light, which is why the ground is not as highly reflective in, say, band 2. We won't spend much time in this class looking at data from bands 5 and 6, however they also have specific useful applications. Band 5 is centered at 1.61 microns. At this wavelength, ice absorbs radiation more than liquid water. This means that ice clouds will appear to be less reflective than lower liquid water clouds, which can help infer the phase of water in the clouds. If you compare this image to the other images from this scene, you'll see that the low-level stratocumulus cloud appears relatively brighter compared to its surroundings than in other channels. Shadows of high cloud, such as along in here, are also better contrasted against the low cloud background. Channel 6 is used for cloud particle size detection, which is an application we will not cover in this class. However, it can also be used to detect hot fires at night. Since no solar reflectance will appear at nighttime, hot fires that emit partially in shortwave wavelengths appear in this channel and are strongly contrasted against the relatively dark background at night. In the next module, we'll move on to looking through the long-wave ghost channels that detect radiation emitted from Earth.